Hey everybody, welcome back. This week we are going to tackle model fit and goodness of fit and effect size for multi-level modeling. It should be a nice build on the things we've already covered. So I'm going to go ahead and share my screen, and we are going to pop over here. Let's see, share here, and then I'm going to pop over to this screen right here. So these slides are available on Canvas, and hopefully they explain a lot of what I'm getting at. So let me start the presentation here. Okay, so this past week, so this is Module 6. In Module 5, we talked about adding random slopes. And you all actually had some really good questions, and these are questions that I actually get a lot in this class about how, when, and why you might choose which predictors should have random slopes. You know, some people say, okay, should we just test all of our slopes as random? And if we don't do that, then how do we decide? Is it just about model fit? Can theory inform this? You know, there are lots of different ways of thinking about this. So those are all great questions. And I would just remind you that this is sort of the icing on the cake. So random slopes, along with cross-level interactions, are kind of the last thing that you test when you, after you've built a model that you think is pretty good that answers the research questions that you are setting out to answer. So my answer would be, if you have what I'm calling a typically sized multi-level data set, and by that I mean you have 100 or fewer clusters, so schools, for example, and if you have less than 1,000 total participants, I recommend using those random slopes actually pretty sparingly. And the reason why is that in a smaller data set, if you load it up with random slopes, it's not going to be very well powered. You're not going to have a ton of statistical power. And it's also likely, depending on the kind of estimator you use and so on and so forth, you can even introduce a little bit of bias into your estimates. So I would not recommend going crazy with random slopes. I would always test the random slopes for my predictors of interest. So, you know, you think about your focal variables that you're most interested in for your study, and that's usually related to your literature review, your conceptual frame. You're trying to find the gap in the literature. So I would start there and test those variables as random, at least. I wouldn't worry as much about covariates, control variables, other things, unless you were in a really, really big data set. So if you have a data set, you know, for example, we have a sample from the high school and beyond data set that is, you know, the full data set's like 20,000 kids and hundreds of schools. That's a data set where you can make pretty much everything random if you want. And it'll be sufficiently powered to find significant random variation if it exists. So if you're working with one of those big longitudinal data sets, then absolutely. But if it's something more reasonably sized, then I would say use sparingly. All right. Okay. So just a reminder of this what I think is hopefully useful slide, which is adapted from a book by Jupe Hawks on multi-level modeling. So this is sort of the process of how you build a multi-level model. And each one of these basically roughly corresponds to a module that we have studied throughout the course so far. So the first thing you do is you start with a null model and you calculate your ICC. We did a whole week on that, right? Then you run what's called a random intercept model and you introduce predictors at level 1. And then same thing, predictors at level 1 and level 2. So this was actually module 4. So the null model was module 3. These two boxes here were module 4. And then last week we talked about including, in addition to a random intercept and predictors, incorporating random slopes of our predictors. So we're not only estimating the sort of fixed effect of the predictor, but we're also measuring its variability, which can be very useful and powerful when used in specific situations. And then of course out here, now R people, this is not a separate step. So if you are using R, you already are allowing for random covariances between random slopes and random intercepts. But Stata people, there is of course another option where you can add that unstructured covariance option to your multi-level model. We practiced that last week, which then allows for just a slightly different way of thinking about the structure of those random variables at the higher level. So you might think of this as the sort of process of building a multi-level model. And I've actually cited this in papers before. I've said I'm using this approach, and this is sort of how I unpacked my explanation of the results. Each one of these was sort of a separate section. So that's a good way of thinking about it. So up until now, the first 5 modules of this course are sort of teaching you the nuts and bolts of how to build, conceptualize, build, estimate, and interpret, and in some cases visualize even, right, if you have a cross-level interaction, a multi-level model to answer your research questions. And there's one other important area that I want to make sure that we hit on, which is goodness of fit measures, which we've been using all along, but I just want to be really clear about what they are and how to use them. And hopefully that'll be mostly a review, because we've been talking about things like AIC and BIC and likelihood ratio testing since early on, right? Since the week when we talked about null models. But I just want to do this a little bit more formally so that you get a little bit more of the conceptual knowledge behind it, and also just as reinforcement for what we've covered so far. In the second part of this lecture, I'm going to talk about effect sizes. So effect sizes are kind of the last missing piece for multi-level modeling. Just like effect sizes in other types of research, things like Cohen's d, correlation coefficient, all these things can be considered effect sizes. This is a way of thinking about the practical significance of your results, or in general, how well does a model explain a given phenomena? And that's really helpful. Effect sizes are things that are very, very helpful in helping particularly a reader who may not be familiar with your topic understand how your model is working, and also how well it's working too. So that's another important component. So that's what we'll talk about in just a moment. Okay, so we're now going to talk about measures of goodness of fit. So goodness of fit, and it's often abbreviated GOF, big G, little O, capital F. So we've used a lot of these before. So we used these, for example, when we learned how to incorporate a random slope into our multi-level model. And we asked ourselves, you know, how is it, does it improve the fit of the model to incorporate a random slope in addition to a random intercept? And so, and again, basically, if we put this all together, we've learned how to build a multi-level model from scratch, right? Artisanal in some ways, right? Very cool. So, and this is the hierarchical approach. In each step of the way, as we go along, we can check whether or not our model has improved by looking at goodness of fit measures. So this is a useful way of thinking about, okay, is my model actually getting better as I progress along these steps? And we're going to talk primarily about 2 goodness of fit measures: the Aka-Ike information criterion. That one's always a mouthful, AIC. And what's called the Bayesian information criterion, which is actually called Schwarz's Bayesian information criterion. But these are more commonly known as AIC and BIC. And then we're also going to talk about a statistical test that basically gives us the same information, called the likelihood ratio test, the LRT. Okay, so for all of these, the intuition is lower is better. And what we're looking for, and I had to bring in Game of Thrones here. The only reason being that Game of Thrones, the abbreviation for Game of Thrones is GOT, and goodness of fit is GOF. But if you watch Game of Thrones, you know that this character Daenerys has a very long, fancy name. And as part of that name, I would like us all to be skilled users of goodness of fit statistics by the end of this. So the thing to keep in mind here with fit statistics is lower is better. That means we're explaining more of the probability space and that our models are explaining more of our outcome. Okay, so we'll talk briefly about the formulas for AIC and BIC. And these formulas actually look fairly similar. So AIC is calculated as -2 times the log, and that's a statistical operation, the log of whatever the likelihood is that was maximized in our model, plus 2 times P, where P is the number of parameters that are estimated in our model. And what is a parameter? This gets pretty important. So a parameter is something that is unknown about the model that is estimated when we run the model itself. So the most common parameters that we estimate in multi-level modeling are an intercept and the betas for any of our predictors. And those are typically fixed effects, right? So we estimate a fixed effect for the intercept, fixed effect for all the predictors, each one. We also estimate a random component for the intercept, a random component for any slopes that we're including as random. Those are also random components. And a random component at the individual level as well. So those are all the random pieces. Those are also parameters that we're estimating in the model. BIC is a similar formula. BIC again is -2 times the log of the maximized likelihood. The only difference is here we're adding log n times P, where before it was a fixed value of 2 times P. And this is going to have some implications in terms of how you interpret these things. So another way to think about this is no matter how many people are in your sample, AIC, it does not impose a penalty or a benefit, right? It's always 2 times the number of predictors. Whereas BIC is going to change, that penalty is going to change a little bit depending on how many people you have in your sample. But again, lower is better. So for any of these, a decrease of more than 3 points suggests an improvement in model fit. If the values stay the same, just get a little bit lower or get higher, that's a sign that your model fit has not been improved by whatever variables you added into the model. Okay, so some quick notes. Both of these statistics are possible because we use what's called model likelihood, which we obtain using maximum likelihood estimation. So remember, maximum likelihood is an estimator. It's the way in which we get the estimates to our equations, and it's sort of a fiddling thing where you're sort of adjusting lots of different possible values, and you end up with a solution when the likelihood is maximized, hence maximum likelihood. And that particular value is the thing that gets plugged in. And we're finding values of our coefficients that maximize what's called the probability surface of our data. That gets into likelihood theory and all kinds of other stuff, estimation theory, which we won't go into now. AIC and BIC both are -2 times that likelihood. Then AIC imposes this 2 times the number of parameters penalty. BIC is log of sample size times the number of parameters. So again, for BIC, BIC includes sample size in its calculation, AIC doesn't. And I'm just going to follow the advice of Garson here, and this is coming straight from chapter 5. BIC, if you have to choose which one to trust, BIC is usually the preferred measure of fit because it's what is called consistent. And what that means is as the sample size increases, it will over time converge on the true quote unquote model. So an estimator that is consistent is generally a good thing. That's something that we want. AIC is not necessarily a consistent estimator. If you have a larger sample, it actually doesn't increase the probability of selecting the best model. So that's why people tend to prefer BIC compared to AIC. So here's the problem. BIC may actually over-select less complicated models with fewer parameters. So in other words, BIC imposes a pretty stiff penalty for making complicated models. So things like random slopes, additional predictors, those are harder to be found to be significant when you look at BIC. And one way to think about that is BIC prefers what is called parsimony or simplicity. And AIC actually leans a little bit in the other direction. It prefers complexity. So it would actually tend towards preferring something that's a little more complex over something that's a little more simple if it's on the border. So in general, we tend to say if you're getting conflicting advice, go with BIC. That is the sort of the safer route, but hopefully you get consistent advice from both. Okay, so I'm just gonna walk through with you a little bit how to do these kinds of comparisons, and we'll look first at Stata and then we'll look at R. So first we're looking at comparing AIC and BIC in Stata. So here we have two models. Model 1 is a multi-level model, and this comes from your content review that you've been working on for a couple weeks, this tobacco health data set. So our outcome is tobacco health knowledge, and all we're doing is controlling for a fixed effect for the prior score. So we're basically seeing what's the relationship between prior score and score at the end of the intervention. And we get our model here, and model 2 is the same exact thing. All we've done is added a random slope for pre-THK. So this is a pretty typical situation. You have a model like model 1 that works pretty well, and then you want to know, should I add a random slope for this given predictor, which is model 2. And the key here is to look for AIC and BIC and see how they change. And in Stata, you run this command estat-ic for give me the information criteria associated with this model. And here is AIC, BIC for the first model and the second model. And if we look, okay, AIC is 4733 here, and it's 4734 in model 2. Okay, so we don't want it to go up as we add a more complex model. We want it to either stay the same or hopefully get lower, ideally get lower. So that's not a good sign. BIC is 4755, and it goes from 4755 to 4761. So it goes up by 6 points. So the decision here, AIC and BIC both went up. No good. We want to stick with what we've got. And that means we would not add a random slope for pre-THK. All right, so a similar model here in R with a different decision. So this is our hostile data. This is the data looking at the soldiers nested within company predicting hostility towards the goal. And again, this is one we've ran quite a bit in different class demonstrations. So here we have a model 1, and model 1 is a good fixed effect model that includes a random intercept at the company level and fixed effects for TSIG, lead, and GTSIG. So task significance, leadership score, and group level task significance. And then our comparison model is the same thing, except we've now, see the TSIG is now included over here. We've now included an additional random component for TSIG. So the question here is very similar. Do I want to introduce a random slope? I have a model that works well. Now do I want to introduce that random slope as well? And so we fit both models. And in R, you get your AIC and your BIC right at the top. So it makes it easy. You don't have to run that extra command. So AIC is 5533 for model 1 and goes down to 5517 in model 2. Aha, so AIC went down by 16 points. That's a good sign. BIC started at 5567 and it dropped to 5562. So it went down by 5 points. So both AIC and BIC went down. That's really good. And the decision here would be we want to include the random slope for task significance. So in this case, we actually would include that random slope. And just a little more info here. So the log likelihood here, this is actually that value that you start with to calculate AIC and BICs. Remember, it's -2 times the natural log of the maximized likelihood. So it would actually be -2 times this thing, times log likelihood. Plus, if we're doing AIC, 2 times the number of predictors. We have how many predictors? 1, 2, or parameters. How many things do we estimate? 1, 2, 3, 4, 5, 6. We estimated 6. And then BIC would be log n times the number of predictors. So log times the number of observations, which in this case is about 2,000. So the raw components are all here, but it's nice that the software calculates AIC and BIC for us, but that's where it's actually coming from. Okay, so that's comparing AIC and BIC across the two. There also is another option, which is using likelihood ratio tests. I like to use AIC and BIC myself because they're pretty quick to interpret, they're pretty simple, and it's pretty easy to communicate to your audience. So for me, it's like, okay, did this model result in a reduction of AIC or BIC? Yes or no? If no, okay, then the model wasn't improved. But some people really like p-values. And you know what? To be fair, don't we all? P-values can be really great sometimes. They can sort of lead us, give us very clear evidence about whether or not we should keep something or not. And AIC and BIC are information criteria measures, so they don't give you a p-value, and they also don't give you any guidance about whether, you know, what you're supposed to do with it. That's all sort of up to you to make that decision. But LRTs, likelihood ratio tests, are a way to get a p-value. And we've run some of these already. So maybe not in Stata, but I think I've already ran these for the R folks. So, so here's how they work. You run your first model and you save your estimates. And what this does is it saves the log likelihood and other info in the memory. And then you run your second model, and again, you save those estimates. And again, you're allowed to then access those estimates later. And then you use in Stata the LR command to compare the two models. In R, I should say, I forgot to update these slides. In R, you would use the ANOVA command or the RAND command. The RAND command is what you would use if you want to know if a random slope has resulted in an improvement. So if you're testing a random slope, use the RAND command. And if you're testing anything else, another predictor, an interaction, you use the ANOVA command. And we've used both of those in previous weeks. So hopefully those functions are not entirely new to you. But again, for both of them, you're going to get a LRT value, a chi-square, and you're going to get a p-value to help you make that decision. So these all produce a chi-square test of model fit. And the degrees of freedom for that test are the difference in parameters. So if you're adding just a random slope, that will typically just be a 1 degree freedom difference. If you're adding a predictor, a fixed predictor, that'll be a 1 degree freedom difference. If you add 3 predictors, that's a 3 degree freedom difference. Okay, so a significant result suggests that the second model, the one you're comparing to it, has significantly less error than the first. So if your test is significant, then it's saying the more complicated model with more stuff in it actually is a better fit. If it's not significant, then it means it's not worth it to go to the more complicated model. That's one way to think about this. And yes, we all love p-values, especially when they're close to the border. Keep in mind, of course, you know, p-values are not the only thing, but sometimes they can be nice. Okay, so here's how you would use this in Stata. So this is the tobacco data set again. And here we have, first of all, this same set of models that we ran last time for AIC and BIC. So here's the model with just prior score, so THK and pre-THK. And I run this, and then I use the estimates store command to call this model underscore one. So this is model one, okay? It's the less complicated of the two models I'm comparing. And then I run a second model here where I add a random slope. And I call this model model underscore two using the estimate store command. And once I've stored those estimates, I can then run this LRTest command, and this is built into Stata. So LRTest model two, model one. So I'm comparing model two to model one. And then we get a chi-square test and a test statistic, which in this case is very small, 0.65, and then a p-value, which in this case is non-significant. So in this case, again, this is the same decision point we got from looking at AIC and BIC. This is telling us you don't need to include the random slope for pre-THK. It does not result in a significant model improvement. Now, the one tricky thing with running the LR test in Stata, these are only work when you are doing a 1 degree of freedom comparison, one parameter different. So that means you can do this for adding a random slope. You can also do this for adding a predictor or taking away a predictor. But you can't, for example, put in 2 or 3 predictors. It has to be what's called nested, which means the two models are 1 degree of freedom different. And the way to check this, you can see the degrees of freedom here and the degrees of freedom here, making sure I'm looking in the right place. Yes, that's where we look. So in this model, we have 1 degree of freedom. In this model, we have 2 degrees of freedom. So that's how you know they are nested, okay? And so if they differ only by 1 degree of freedom, then you can do this LR test thing, which allows you to make the distinction. Okay, so R people, it's a very similar approach. So here, again, we're going back to the hostility model. So here's the fixed effect model with T-sig lead and GT-sig, and then a random intercept. So there's that model. And then, so the nice part is when we define this, remember R people, we call this model.1 ahead of time. So we already know this is model.1. And here is model.2, where we have added a random slope for T-sig. And then we run this command down here, which comes from the Elmer test package, Elmer test, and this is called RAND, so R-A-N-D for random effects. And that compares single term deletions, what it calls single term deletions. So it's comparing our model with no terms deleted, which is our actual model here. And you see the AIC is 517.3. Comparing that to a model where T-sig, the random slope, has been deleted. And notice the AIC is 5533 in this case. So it actually went down. It went from 5533 to 5517. That should be significant, and it is. The LRT and the p-value there gives us our result. So we get a very, very small p-value. So we have additional support using the likelihood ratio test. Alrighty. So in the next part, I'm going to talk a little bit about effect sizes, but I think this is probably a good place to pause. So we're going to pause there, and we will come back soon.